group theory, and it's a vast subject. But the kind of things which we need actually is available in the textbook which has been mentioned for this course. This appendix lists actually many more results than what I talked about, and most of them are given as elementary exercises. Okay, so the proofs are not complicated, maybe 2-3 lines of arguments, but you should think through it in your head, because these are all concepts. Even though they are simple, takes time to digest. And so just go through this appendix and try to understand how various things are constructed and what is the logic and things like that. I will give some more labels today which are useful. So one of them is just composition table, which explicitly defines the whole group. Okay. Because what we need for the group is the list of elements and the result of combining them. So what this table essentially does is, it's some particular operation. This is the way it is written. Set of elements here. One side I, the other side j, and the table is basically an array of this product. So it's one is a row index, the other is a column index, and you give the whole list, and that is the complete definition of the group, because group doesn't need anything more. And the way this thing is generally structured is the first element in the list is always the identity, because no matter what you do, it is always there. And that means the first row and the first column of the table is nothing but the list of the elements. Okay, so first element is identity, and first row and column is list of elements. What happens in the other rows and the columns, that is also very easily figured out from the fact that this structure is such that inverse exists. So it means that Gi going to Gi star Gj, it can be considered as a one-to-one map. Okay, multiply all the elements by some constant, it will change them to something else, but because there is an inverse, it has to be one-to-one mapping. It cannot be many-to-one or one-to-many. Okay, this is And now what does it tell you about this table? Whole list of elements, you do a one-to-one map to something else. You are not allowed to map money onto one or one into many. But that means all the other rows and columns are nothing but permutations of the elements. There is no other one-to-one map you can construct between one set of elements and another set of elements. Both are the same. All you can do is rearrange the order. So these rows or columns are and this is a very powerful constraint in understanding the structure of the group. Okay. So let me just give trivial example. So the group which I mentioned last time was Z2, and it had the property, whatever I call it star, that there was one element which was the identity and the second element which is different than identity, let me just call it G. And so this now becomes very simple. What is G composed with G? It cannot be G because the map will not be one-to-one. The only choice is this is I. And that's what happens. You look at any row of column, it is just permutations of what is there in before. I can give a next one, let me call it Z3. Again star, I, some non-trivial element G, and what the third element can be? Well, I have to obey the composition rules. I can certainly calculate G square. If G square becomes identity, then it becomes this group. It's not that. So I need a G square. But then what does the structure Z3 tell me? That cube will become equal to identity. And so the G square happens to be the same as G inverse. And that is a 3-element group, and now you can fill in all the list I, G, G square, G square, G times G is going to be G square, G times G square is going to be identity. Nothing but permutations will come. G square times G is again identity, and G square times G square is G to the 4, which will reduce to G. So this kind of structure works. And remember, I am not using anything complicated, just the properties which was defined by the rules of the group. There has to be identity, there has to be a composition rule, it has to be closed, and there is an inverse. And this is a very powerful way of explicitly showing what these constraints produce. Okay. First time you encounter this, you have to do it by brute force, and then you will get used to the arguments which are more formal. Okay. So this is a useful concept, composition table. It tells you what all kind of things it can be done. And actually what I erased, which was over there, was a composition table for a different group. That's another example. I will not go into that right now. Okay. Another concept which is useful is called subgroup. And concept is rather straightforward. It is a subset of elements which are closed under group operation. And we are very familiar with this kind of stuff, at least in the usual examples of numbers which I am giving over here. If I say, look at the list of all integers, then under addition, 0 is the identity and 1 is a generator, so I can reach any number by keep on adding 1 or minus 1. But I can also now look at a subset of this, which are say all the even numbers. And I can reach all the even numbers from 0 by taking steps of 2. And I will never reach any of the odd numbers by doing that. Okay, so then all the even numbers are a subset of the integers, and so the collection of all the even numbers forms a subgroup of the original group. Okay. It can be, so all even numbers are perform subgroup of integers under addition. Actually, this example turns out to be, yeah.
Distribution should not be infinite, because if you just take all the positive integers,
I'm not taking positive integers.
but they're still closed under the group. So the positive integers,
Yeah.
including 0.
Then I have to do modulo something.
Yeah, so subsets of elements which are closed under group operations. The positive.
I said all integers. I did not say positive integers.
I meant in definitions. You need inverses.
Even numbers positive or negative.
Yeah, I mean when you say subsets of elements which are closed under group operations.
Yes.
Like if I just take the positive, all integers.
Yes.
Are the positive integers including 0?
Yeah.
Are a subset of the group.
No.
It's a subset.
No. The inverse doesn't exist.
Yeah, that's what I'm saying. You're not.
Yes, I'm not saying positive integers. I said all integers.
The example I agree with. I'm just disagreeing with the definition.
I should, instead of just saying closed, which not just closed, it has to obey all the group properties. This turns out to be more powerful than just under the operation of addition, because I also know that if I take any number, say 5, if I add any two numbers which are multiples of 5, I will get a multiple of 5. If I multiply two numbers which are multiples of 5, I will again get something which is a multiple of 5. So this kind of numbers and subset is actually more general. It is not only a group, it is what I last time called a field. And it will obey the rules of two operations, not just addition, but both addition and multiplication. That is a little bit beyond the point, but those kind of things are useful in many circumstances. But let me give something more explicit examples which are, yeah.
In group composition table, we are indirectly saying that the group is complete because
No.
Because I star G and G star I have the same value. So they should
No, this table in this particular case is a transpose gives you the same thing, but in general it does not have to be true. These are two simple examples where that.
Yeah, but I mean, if you are expressing in that form, then we are indirectly saying that G star I and I star G are equal.
No.
Or G.
This element in general does not have to be equal to this element. It is not necessarily equal to a transpose in general. In this particular case it is, but that is not true in general. It need not be commutative. The order matters. So there are two particular objects which are useful whenever you are talking about matrices. And we'll talk a lot about matrices as representations of the group. And those two properties of square matrices are a determinant and a trace. So these are things which you learn in high school. Determinant, there is a specific combination. It's a product of all elements with some plus or minus sign in some order. And trace is nothing but the sum of the diagonal elements of the matrix. These two objects turned out to be very useful. So let me include one of them over here. So the property is, for the determinant, is determinant of, say, two matrices is nothing but the product of individual determinants, and determinant of inverse of a matrix is one over the determinant. And these are the objects which appear also in the definition of the group. How do you combine two and how do you take a inverse? By staring at that equation, you can immediately realize that representation matrices with determinant equal to 1, where these identities become trivial, both this and this. The 1 is a reciprocal of itself, and you multiply to 1, you will get 1. And so this will form a subgroup. It will be a subgroup of that particular representation, but it can be expanded because you can do this for any representation. So factor it out, and then all the representations combined will define the group, and you can cut it down to certain level that whatever this representation I'm talking about, I can put determinant equal to 1. Simplifies the construction a little bit, and that turns out to be very useful as well. And well, there are more labels which, if you look at books, you will combine, but I will not go into detail. There are related I don't need it right now, so I will just mention the name and skip. There is something which are called classes, something which are called cosets, etc., etc. And they are like the elements which are left out when you remove a subgroup. I can say all the even numbers form the subgroup. What are odd numbers? Then I have to do some construction to define that particular set, and if you try to do that, these are the labels which appear. I'm just mentioning them because they will be quoted in textbooks right now. I have no need for that, and I kind of skip it. Okay. So this is some definition, and there is the other properties of the matrix which is useful, and that I mentioned as a trace. So the notation is it is some quantity in some representation related to the element, and this is equal to the trace of this matrix M for representation R corresponding to the element G. So this is a matrix, you take a trace and you get a number. And since the matrices are in general complex entries, the trace can be complex in certain situations. Okay? Doesn't have to be all the time, but it can be. But this is a definition, and how it is useful for that you have to do some algebra, but these characters, they obey various orthogonality relations. In the same sense, they can be listed as a table. It's another kind of table. This is called a composition table. This will be called a character table. But again, you will find many descriptions, and I will for some group, this is a list of the elements, and this is a list of the representations. There are many representations for the whole group corresponding to matrices of different sizes. There can be many representation of the same dimension also. And what is listed here is the sky of R of Gn. And various orthogonality relations then correspond to, this looks like again a matrix, how are the rows related, how are the columns related. And one can prove any general theorems about this, which are useful in various contexts, just like this. Here it is just a permutation between going from between rows, here they are orthogonal in a certain sense. And that is something to remember. To be able to derive these things, it takes some effort, so I'm not going to do that. And we'll see when the characters appear in some particular examples, we can deal with that, but that will be in a context of a fixed group. For some simple group, you can write down what these things are, and let me do that at least for the binary group which you are dealing with all the time. So what does this table look like? There are two elements. One is identity, and another is the same second element with G square equal to identity. What are the representations? So one of the representation is always there, which is the trivial or the identity representation. And where every element is mapped into 1. Okay. And trace of 1 is 1, nothing more complicated than that. So this just comes out to be 1, and the second representation is what you get by parity or reflection, which I mentioned. If you reflect twice, you come back to where you started. So that is this constraint here saying that G square equal to identity. And what are the properties of this parity representation? Well, it follows from the group elements. Last time I gave a representation where the true group elements were given as 1 and minus 1. And so this is a one-dimensional representation, and all that appears as a trace is 1 and minus 1. And here now you can see that, well, this is a very trivial example, but these two rows and columns are orthogonal.
Here we are talking about one-dimensional matrices.
Yeah, for one-dimensional matrices, trace is equal to the number.
In the first row, second column, why did 1?
Because identity representation maps all the elements to the identity matrix. And trace of identity matrix in one dimension is 1. It's a trivial representation, but that is true, and this will remain true for any group. That trivial representation, the whole row will be just 1, nothing more. So these are the, well, some properties. There are many more things you can do, but I can leave it at this particular state and introduce the other important concept which we need is that of a physical state. As I mentioned last time, group theory can be completely defined in terms of transformations, and they are given as matrices. But in linear algebra, we know that I can define the matrix as a transformation on a vector. So if I take a vector multiply by matrix, it will give me another vector. And even though for discussing matrices that vector is not needed, that vector is very useful in physics, it maps to the hardware. The group is an action on the hardware which transforms its properties, but what is a physical state? It is on which the group performs transformations. So this is a so a vector is a matrix so this is so we will be extensively using this language where the state which is represented by vector, it will refer to something literally present in a physical system, whether it is a bit or a qubit that defines what kind of system you are going to deal with. But for example, a bit can be represented as a two-component vector on which you can perform various operations. You flip it, you transpose it, whatever it is, various kind of thing. And in qubit, it will become again a two-component vector, but it will turn complex. And we'll come to that in a little stage. But this is the concept which is very useful, and it allows me to define something extra, that there are certain transformations that preserve the norm of the vector. They are important, and the reason for this is again some kind of conservation law. That the length of the vector is something which is fixed whenever you are doing this particular transformation. And it is important because the norm of the vector will be some conserved quantity in lots of different applications. And now what that tells you, it restricts the choice of what are the matrices. So let me I'll have to introduce some notation. So this is state, that's typical quantum notation is the one invented by Dirac. It writes variable in this angular bracket. And then I need a what is called a conjugate, or actually more Hermitian conjugate, sometime also referred to as an adjoint state, which is written with this brackets reversed. This is just a notation, but if I literally expand it as a column vector, so this is column and this will be a row. So in usual linear algebra, you go from column to row by taking a transpose. But here we will be dealing with complex numbers, and so the conjugate is actually defined as a complex conjugation and you have to perform both these operations. So you go from a column vector, transpose will take to a row, and then you take a complex conjugate of all the elements in the vector. Okay. So that is defined as either the adjoint vector or a Hermitian conjugate vectors. And with the definition of vector, there is now comes a definition of what is called as a inner product or a dot product, which is generally nothing but multiplication of a row by a column. You contract it and you get a number. Here it will have structure like some adjoint vector and some regular vector. You contract it and whatever you will get a number. But because you are dealing with complex number system, this will be a complex number, and this is generic property. So then of a so-called vector space, so there is a label which will be appearing all over the place as well. So linear vector space with complex coordinates and inner product has important uses. And it's called the Hilbert space. There is more refined definitions than writing it this way, but this is just to make it explicit. What do you mean by a Hilbert space which will appear all over the place? It's a vector space which means you can assign various coordinates. The coordinates have complex values, and using those complex coordinates, you can construct an inner product. So if this machinery exists, whatever that system is, we are going to call it a Hilbert space. And that turns out to be very useful, and it allows me to give explicit meaning of what is the norm of a vector. Well, one of the norm, whatever it is, which appears automatically from this definition, is a so-called quadratic norm, which is nothing but the length of the vector. Dot product or inner product of the vector with itself. It gives the usual Pythagorean theorem type of structure in a Cartesian coordinate, and that can be taken as a norm. It's a quadratic norm because it's the square of the length of the vector. But this is fine, and this is used also very frequently because it will get tied up with this conservation rule when we come across. But all this stuff gives me some extra leverage to restrict the type of matrices that I can deal with. So what are the matrices which preserve the norm? Okay, now I can explicitly construct some vector psi, I perform a transformation. So that will give me a new object which is m times psi. But then I want the norm to be the same. So I take a new notation will be needed, but that is fine. Let me just m times psi dot product with m times psi is and now I can use the elementary linear algebra of rewriting this m as an action on this particular type. It's just a product of the matrices, and it can be also written as psi in the usual real space. If I take the matrix here and put it on that side, it will give me a transpose, but in a complex space, it gives me the adjoint. And so I land up with this particular structure where, the notation which is frequently used, it's a complex conjugation and transpose both of them together. So this is also called Hermitian conjugate, whatever I wrote somewhere here, or the adjoint transformation. This was the mapping for a vector. This is the same transformation applied to a matrix. So that's what it is. I'm doing just a linear algebra. The same transformations can be defined in a list of vector coordinates, and it automatically generalizes. And when I say the norm is preserved, this quantity equals to this, it means that whatever is here is an identity matrix. And matrices of this particular structure are called unitary matrices. And can write this in a different way. Another way of writing this is m dagger is equal to inverse. The same thing. I can apply M inverse on both sides of the equation and I get a relation like this. So unitary matrices have a special property, and that is very useful in dealing with transformation which preserve the norm of the vector. Of course, we will take further advantage to impose this condition as well in what we deal with, and so unitary matrices can be further restricted by saying that the determinant is equal to 1. Because it is going to be a subgroup anyway, so and then they are called spatial. Spatial just means that the determinant is equal to 1. And one of the frequently used example is what I mentioned last time. It's the group or unitary transformation in two-dimensional space. Generic notation SU2. And all the analysis of quantum computation will start with action of SU2 on a two-component vector, which is we call the qubit, and you will perform transformation on the qubit to go from one state to another, which will be called computation. So this lies at the what you call fundamental level of the whole construction which will be built, and one should learn quite reasonably what this particular group is. So I will again write down some elementary properties which follow from all these relations which I mentioned. So, okay, what is this stuff is 2 by 2 unitary matrices. With a determinant equal to 1. Let's just construct it explicitly. It makes all kind of things obvious. So unitary matrix with a matrix times is a adjoint will give you identity. That means I take a row and construct this, which will produce this mod square. So each row and each column will have a fixed magnitude, and since right hand side is identity, that magnitude is 1. So I take all the elements of any row or any column, take a absolute value square and add them up, it should give me 1. So that gives me, now I'm just going to list it by brute force. Let the first two elements be alpha and beta. I don't have any restrictions right now beyond that. But one constraint which already say that norm is going to give identity, which means that this has to be satisfied. And this is again generic complex notation. Mod is the absolute value of a complex number. Given this, now what can I say about the second row? Well, I already have a restriction here, and that is of orthogonality. Because the product is identity. If I take a row or column with different indices, it should give me 0. So these two numbers, there are not many ways to make the product non-zero. If the other row has to be just this thing ordered reverse with the minus sign. So when you take a product, it becomes 0. But the product is defined after taking the Hermitian conjugate, and so it appears, or rather the notation I will use is minus beta and alpha. There is an overall sign which I cannot tell because the dot product is 0. If I put anything in front as a normalization factor, it cannot be defined by saying that the orthogonal product is 0. Let me ignore that. I will just say it in a couple of minutes and make a product so that this, if I multiply this with this and add it up, it is giving me 0 up to an overall normalization constant. But I am doing this in a complex space, so these numbers are actually complex conjugate. So when I take this dot product, I have to take one row and the complex conjugate of the second row and multiply them, then whole thing will become 0. So this choice, now you can trivially see that it will make dot product of not only the two rows equal to 0, dot product of the two columns is also equal to 0, and the overall constant I kind of cleverly eliminated because that constant will contribute to the value of the determinant. What is the value of the determinant? It will be alpha square, mod alpha square plus mod beta square. If I have a constant, it will go into the determinant, but I want determinant equal to 1, so I threw out that constant. So it is the same condition. So this is normalization and determinant. Here the columns and rows are orthogonal. And this is the most general 2 by 2 unitary matrix you can write down with determinant equal to 1. It involves 3 parameters. Okay. 2 complex numbers, but 1 constraint. And how will you visualize it? Well, it's kind of, again, coming from this identity. I can write a complex number as a mod alpha square is real part square plus imaginary part square, another real part square plus imaginary part square. So it is 4 real numbers squared add up to 1. That is a sphere in 4-dimensional space, the surface of a sphere. That's the Pythagoras theorem. And because it is 1, it is unit sphere in 4-dimensional space. Sometimes there is this notation, you might find it is called S3. Doesn't matter. So this is explicit geometrical visualization. Also there is algebraic expression. You can do it in geometry. And now what can you do with the sphere? Well, there are all these unitary matrices. What you are going to do is rotation. Just like do it in lower dimensional spaces. You perform a rotation. Rotation doesn't change the radius of the sphere, but it takes one point here to another point over there. And that shift of the point is going to be the unitary transformation. That's it. The most general parameterization of what is possible with these 2 by 2 unitary matrices. There is another notation which is quite common, and it rewrites this quantity in a different manner, and the notation was invented by Pauli by defining a very specific basis. This is fully general. I am not defining any basis. I can now choose, in the 4 dimensions are there, some coordinate system. And the common coordinate system is the one used by Pauli. It has 4 elements. One of them is identity matrix. Then, both the labels are used, so I can write it at 1, 2, 3, or sometimes people also write it as x, y, and z. And sometimes this is written as sigma x, sigma y, and sigma z, because the Cartesian coordinates are easily described using x, y, z notation instead of 1, 2, 3. That's okay. Why did he choose this particular basis? There is a reason for it, and they have certain nice properties. So all these 4 matrices, so I will denote with just mu equal to 1 to 4. They are all Hermitian. If I take this conjugate transpose, they will come back to themselves. But on top of it, they are all square roots of identity. And this also turns out to be very useful in doing various algebra. Take square of this, you will get identity matrix. Then there is a third property, which is a kind of commutation rule, but which is also quite useful. That what will happen, okay, here I have to take a slightly different system. So I made a distinction that there is a Greek subscript. If I use that, I go over all the four possibilities, and if I have used this Roman subscript, then I will look at only this 3, which does not include the identity. So this is a composition rule in the sense of group. What will I get if I multiply 2 of them? And the choice is such that the system is closed. So I multiply 2 of them, I will get one of the other ones. Of course, if one of them is identity, nothing will change, it will remain the same. So this is only related for the other 3. And here, if the 2 indices are equal, I will get identity, just repeating this statement. But if they are not equal, then I will get a third matrix with a factor of I and an antisymmetric symbol. So this is again something which you have to remember from the vector space language. The epsilon symbol is a permutation which defines odd or even sign depending on how many times you look at it in some order. So it's sigma, the standard notation is epsilon 1, 2, 3 is equal to +1, and if I do epsilon 1, 3, 2, then it will become -1. So any what you call exchange will flip the sign of this epsilon ij. And that means if the indices are not equal, the epsilon symbol tells you that the matrix is going to anti-commute, which is sigma I sigma j is equal to minus sigma j sigma I because of this epsilon symbol, and that you can easily verify. You multiply this with this, and the reverse order, you will get opposite signs. So this is a basis which is going to be very useful in denoting this object in a different way. So I will just write down explicitly what is this M. Now use this Pauli basis. So M is equal to real part of alpha times I plus real part of beta times sigma 1 plus imaginary part of it's a minus, fine actually, but there is an I here. Okay, that is how we define the imaginary part or not, doesn't matter. So I have to give a definition that I is equal to real part of alpha plus I times some convention of the imaginary part actually also refers to a real number, and then I have to put some signs which take into account whatever is here. So this is a sign change because this one has a minus part here. I think can write it in this particular forms, and then you can relabel this thing with a shorthand notation. Where these various components of are these nothing but the real and imaginary parts in some form or the other, but the I have kept explicit. And then the constraint just becomes that Pythagoras relation in 4 dimensions. So that is just rewriting this in the Pauli basis. 4 coordinates, they are orthogonal, and I write a total length as equal to 1, which just gives the same geometrical picture, but now there is an explicit basis. And in that basis, you will generically write this 2 by 2 unitary matrix as identity plus some coefficients times the Pauli matrices. The coefficient of the Pauli matrices here are all going to be imaginary. There is a, well, basically that's the convention. So, and now you can verify everything easily, even in this basis. You construct M dagger M. This will just become, these are real, these are matrices are Hermitian, so the only thing which happens is the sign flips, and now you can easily check that M dagger M will give you identity. Multiply this, use all these commutation rules, and everything will come out to be just this particular condition. I think I messed up something over here, but it's this. Yeah, this is real types of beta is 2 signs are opposite because this is star. So this will be real beta, and to get this opposite sign I have to multiply this thing with plus I. So it is, this is sigma 2, and the imaginary part has the same sign on both sides, but there is a, this is equal to 1. Okay, that will fix the overall factor of I coming in front of everything and give to this notation. So yeah, this is, my time is up. This is all linear algebra, and we will use a lot of this properties of SU2 and Pauli matrices all over the place in doing various calculation. There's nothing complicated, but you have to become familiar with the notation. So yeah, I will stop here.